Good afternoon, everyone. A very warm welcome to all the panelists and participants. Before we start, a quick note to all the participants. To get the best audio and video experience, make sure that you are connected to a stable internet connection. If you are facing any audio issues, please ensure that you have selected computer audio option from the control panel on your right hand side. If you have any questions during the webinar, you can register your questions in the question section on the control panel. We request you to mention the initials of the panelist to whom you want to address the question to. We request you to keep the questions restricted to the topic of discussion. We'd also be conducting polls in between the presentations. So the moderator would be informing you once the poll is active. You can register your opinion in the poll questions. So now I'll hand over to Manas sir to please take over. Manas sir,
Very good
over to
afternoon.
you.
A very good afternoon, dear colleagues, my fellow experts and panelists. I think I will give just 2 minutes more, maybe 1 minute more to start today's event, which is on a very interesting topic, electric vehicle charging infrastructure and the power quality dimension of it. The reason that we are committed to the climate change goals as a nation, and there is a huge thrust. So we from Asia Power Quality Initiative, we felt that this is an interesting area where the community might like to hear the experts' opinions, views, and update themselves onto the various aspects of power quality which can be faced by the electricity distribution system when EV chargers come on. So with that, let me start today's webinar. A very warm welcome to each of you who are taking their precious time today to be with us during this particular webinar. The demand for public electric vehicle charging infrastructure in India is heading northwards. It's continuously increasing, and the public charging infrastructure we all are seeing regularly from the news reports are financed by government entities in various states. But poor power quality issues are possible, and they can really act like a speed breaker which can break this ambitious backbone of EV introduction in our country as a clean option for climate change mitigation technique, one of the clean options. With the high cost of charging stations as of today, the power quality concerns will define the reliability and the sustainability of EV infrastructure, and therefore it will be very crucial to the speed at which India can reach its EV ambitions. So with that in mind, we thought it's an appropriate time for EPQI community as well as electricity distribution community to gather together to talk around the power quality dimension for EV charging infrastructure. And therefore, we have organized today's webinar. I once again welcome you all and happy to introduce Mr. Vikrant Vaidya, who is going to be the moderator for our session today. Solutions. He is a practitioner, he is a teacher, and he is a thought leader. With more than 2 decades of experience into this automotive area and working with global OEMs like Tata Motors, General Motors, Jaguar, Group PSA. He has a master's degree in energy systems engineering from University of Michigan and has under his portfolio few recognized innovations in electric hybrid powertrain configuration, battery farm sizing tool, and such, including the algorithm for EV batteries for frequency regulation. He has a green belt certification by General Motors. So you might say that he is one of the karate master into the field of EV field. Welcome, Vikrantji, and the floor is yours from here on to take it forward. Thank you.
Thank you, Manoj. Just share my screen. I hope it is visible.
Yes.
Okay, great. So let me take you through some of the context that is to be set for today's discussion, and then that will be followed by introduction of our esteemed panelists. So coming from the requirement or the motivation, as Manasji was also talking about in our context, is basically how the business models and technology models are evolving and converging in EV space. So the EV itself, the adoption of the EVs is being encouraged. It is being driven from the government as well as from the climate perspective. And then just the EVs alone are not sufficient, because if my power generation, which eventually charges the EV battery, is fossil fuel heavy, it still just displaces the emissions or the pollution to another place. So along with EVs, what is also important is sustainable and renewable resources like solar. And then most of the charging of the EVs is expected to be off grid. So the grid storage, as well as the grid, as we are going to talk about the power quality as well. And then going into some I won't at this point in time call them very futuristic, but vehicle to grid or vehicle grid integration kind of concepts, how ready we are, and what would be the next steps. So when we talk about electric vehicles, one of the primary concerns that the end users have is the charging. And it is not just the range or the charging time, but also the availability of charging infrastructure. In many of the use cases, it is not feasible to just depend on home charging, overnight charging, particularly when we talk about public transports, when we talk about shared transport, when we talk about new ownership models which are evolving over time. And that is why this charging infrastructure is not unidimensional, like just one type of charger from your domestic outlet. No, there will be public charging stations, and there will be models like battery swapping, which will enable even faster turnaround recharging. And then there will be fast chargers, particularly for heavier vehicles, four-wheelers and buses, where the slow charging absolutely is not practical. And all of this will be playing on, most of this will be supplied by the grid. And some of it, very small amount of it could be from microgrid or off-grid. So looking at the EV sales scenario, so there are two scenarios that we analyzed in one of our case studies. And you can see one of them, scenario one is the optimistic scenario, and scenario two is the pessimistic scenario, in which by 2030, 10 years from now, we will be somewhere between 100 to 30% of penetration of the EVs. If we look at optimistic, it will be all the sales from 2030 onwards would be electric. And even in the most pessimistic scenario, they will be not less than 30% of the total vehicle sales. And then total EVs on the road by that time, or in other words, we call them fleet, it will be of the order of millions. So anywhere between say 100 to 250 million vehicles will be on the road in India, electric vehicles on the road. And the share would be somewhere between 15 to 40%. And then looking at the batteries, so there will be the majority is expected to be integrated lithium-ion batteries, where you have to depend on charging your vehicle, and then there would be some use cases where you would have a swapping and range extending batteries, which can be plugged in and out of the vehicle as required. And this is in terms of capacity, but in terms of users, the swappable batteries could be as high as 30%. That is what is envisioned. And then we also have charging infrastructure projections. So basically the mix of charging would by 2030 would look something as indicated in the graphic here. Predominantly home chargers, because although the EVs would have a decent penetration, it would be still early days, and a lot of people would still depend on home charging. But then public charging infrastructure would have started big time to ramp up, and then the swapping and the range extender making up around 5.5% of the pie. And then the impact on the grid, because most of these, if not all, would be actually depending on the grid for charging, whether it's at home or in public charging stations, or even if you are using swappable battery, they need to be charged. So all of that would put some amount of load on the grid. So these are the projections in both the scenarios. So around total electric consumption wise, it would be around 4 to 7%. And then the peak load, the power requirement wise, it would be around 20 to 27% is what is envisioned. Having said that, we always hear people talking about balancing the energy and the peak power demands. That's what I also talked about in the previous slide. But that's not all. As Manasji was previously mentioning, this ghost of power quality, and why it is called ghost is because it tends to be sometimes overlooked. But it is also a very important factor to be addressed, both in selection and sizing of charging equipment, as well as from the supply side in terms of regulation. So some of the major power quality related issues are voltage. Voltage, I think, irrespective of the background, all of us are aware what effect a continuous low or high voltage can have, or surges can have. There is also frequency which plays a role, and it is usually because of the large transients in power demand. And then the harmonics, which is basically the distortions in the waveform the supply current waveform, and this can cause adverse effects in the equipment, both in the distribution as well as charging infrastructure. So more than the demand magnitude, the power quality is affected by the transients in the demand. That's what I want to emphasize in this slide as well. So these are basically the universal charging options which are evolving. These are bands. These are not the exact number which are applicable globally, but these are the kind of orders of magnitude of charger power as well as voltage and current that we would see globally as well as in India. And then which of them are applicable to which kind of vehicles. The bottom grid shows this. And the key takeaway from this is, as you can see, we have orders of magnitude of 10 to 100 kilowatts. And just simply turning on or off one charger can induce that kind of transients in the supply system or in the demand. This is just talking about the public charging infrastructure. But public charging infrastructure is what is expected to run most of this fast charging equipment, because home chargers would be mostly the slow charger type, which would be low power. Although low power are also, you can see it is a significant power. Typical household connection in India is around 3 to 5 kilowatt, and the charger alone can add that much. Even a slow charger can add that much of peak power demand in the grid. So coming to the impact on the daily demand. So this is a graph which has overlaid the projections of how many vehicles would be plugged in, or what percent of vehicles would be plugged in into what kind of charging system. So we have home charging, office work or institutional charging, and then we have recreational usage, so mall or any other parking. They could have some charging points, and then public charging stations where you subscribe or you pay for the usage. And I have mapped up two scenarios in which in the middle graph I only have incorporated the home charging, and then the bottom one has the public charging system also. And you can see in the middle graph that the transients are more or less following your base load or the base case. So base load is without the impact of EV in blue, and the orange one is what is with EV. And the bottom graph, it is EV along with the public charging, and this is the kind of transient which is expected to be induced because most of the public charging station, although their percent is very small, they are all fast chargers with very high wattage as compared to the home chargers, and these are expected to bring in these transients and demand. Going to harmonics in terms of monthly transients, another case study that we had done along with PRDC and GIZ. You can, I won't go into explaining each of these graphs in detail, but the key takeaway here is you can see the odd and even harmonics. They are manageable as per the IEEE limits that they have put forth in their guidelines. But that is something you would have to watch out for, because you can see in the scenario 2 here, we are approaching the thresholds. Another aspect, as I mentioned in my first slide, is the vehicle to grid preparedness. So vehicle to grid is essentially a two-way communication system in which the vehicle also responds to these power quality issues, and it can either defer or throttle its charging based on the power quality scenario, as well as other aspects. So this vehicle to grid integration, or vehicle to grid as it is called V2G, this is something we have to be prepared for, and it is something which will be coming. And the basic technical feasibility seems to exist in our country, but there are very crucial further steps required, which include identification of pilots, detailed studies on feasibility in terms of commercials, in terms of communication and IT, and so on. And then the frequency market need to be developed. Grid frequency regulation is something which a lot of us are still not aware of, or not have been working on. And I heard recently, I think about 3 years ago, uh, uh, the Central Electricity Regulatory Board has come up with some guidelines and roadmap for the frequency regulation. And then we have to develop standard communication protocols for the distribution companies to work with this VGI platform. And then smart control on the charging, which could be linked not just to time of usage, but also based on other metrics, like as I was saying, the power quality in terms of supply, and the other aspects of charging. So these are some of the concerns that I thought of setting and addressing to our esteemed panelists. So with that, I will also go through with the introduction of our panelists. So Ashok ji is our first panelist, and he is the Chief Engineer of R&D Division in the Central Electricity Authority under the Ministry of Power, Government of India. He is a researcher, he is a planner, and he's a whiz at policy and standards. And then he has more than 2 decades of expertise in power as well as the electrical domain. He is a leader and member of several Government of India committees looking at electric vehicle overall adoption, as well as enabling the adoption through charging infrastructure. And then he has a lot of deep insights on how the technical aspects of transmission and distribution affect the use cases, particularly for electric vehicles. And we would be eager to hear from him on these aspects. And he also spearheads a lot of initiatives, cross-functional initiatives, in terms of framing policies, in terms of setting up standards and guidelines across different domains. So welcome, Ashokji, and hope to hear from you. Our other panelist is epcohorstmann. He is from GSRI, the Dutch wing of GSRI. And then he has nearly 3 decades of experience in installation sector, in policy functions, in operational and other aspects of distribution as well as power. And then he is currently acting as a bridge between innovation and the market, a very important interface, or very important connect, because a lot of times the R&D or the innovation can be disconnected with what is the requirement in terms of the delivery. And then he is driving the vision development. He also drives the business development, arbitrations, research. And then his specialties include energy in the operational phase, innovations in the installation sector, and he has a lot of experience in these areas, uh, dealing with complex issues. And we will look at his presentation, and you can see how very data driven and ground level insights he will provide to us today. So welcome to EPCO as well. Before we start with the speaker address, let us have one quick survey. So I think Pranav, if you can pull that up, I will stop sharing. So yeah, I think most of you have started responding. So the poll question is in front of you is, are you aware of the power quality regulations? And sorry. I think you will have another 15 seconds or so to respond, and then we will publish the results.
Hello, Vaidyaji.
Okay.
Hello.
Yeah.
Can
Yeah,
I
I think
start now?
Ashok, yeah, we can see. Yeah, sure. Go ahead.
So basically, the context has been set, and it is quite clear that the electric vehicle will find its place in the Indian roads and in the Indian economy. Great efforts have been made by the government. Am I audible, Manasji?
Yes.
Yes, sir.
So voice is clear, I hope.
Yes.
So great efforts are being made by Government of India so that there is a sustainable future of the e-mobility. It is with the two aims, that one is reduction in the pollution as well as provide the cheaper mode of the transport in the long run, at least in terms of the running cost. So let me come directly to the topics, because there is lot of background and lot of policy issues have been taken, lot of initiatives have been taken, that how a strong economy can support a faster mode of the transportation. So what is the potential roadmap for e-mobility? What in our scenario, that is the Indian scenario, what we have thought is that there should be demand creation. A demand should exist for the product. For that, there are the government policies in place, and depending on the regular feedback, the policies are getting updated and modified. In the initial phases, government has thought of providing the subsidies also, different type of the subsidies at different levels. In the purchase of the vehicles, in terms of the charging also. And there are certain mandates that office vehicles, government office vehicles are presently running on the internal combustion engine mode. So there is a mandate that these vehicles will be converted into the electric mode. Then supply side interventions have been there. Investment by OEM is also there. They have been attracted towards the making the investment. Facilities are being provided so that the development plan keep on continuing. A lot of efforts is being made on the R&D efforts. It is purely by the governments also, and it is in collaboration with the industry also, and a consortia approach is also taken. So infrastructure is necessary. There may be large number of vehicles, but they will not be successful unless the charging infrastructure is in place. So a robust and distributed charging infrastructure should be in place in the cities as well as along the highways and the roads. So definite plans are there for that. Creating consumer acceptability. How the consumers will accept. For this, government under the aegis of Bureau of Energy Efficiency, Goal-Electric campaign is going to be launched. And the Bureau of Energy Efficiency has been appointed as the central nodal agency for this implementation purpose. And in the states, there are the state nodal agencies who will be accepting the applications from the implementing agencies and approving them. Technology and application and technology development and the acquisition. This is necessarily a continuously going on process for making the continuous improvement. Then local manufacturing capacity with the aim of Make in India program. So by chance, I am looking after the Make in India program also of the MOP, and we put lot of emphasis on several things, not only the finished product, but even also on the component parts. That is more important. So e-mobility roadmap drivers, what are those? First is establishment of EV charging infrastructure on a wide scale, so that people are not facing the troubles. People are not facing the hurdles in getting their vehicles charged. Creating business models for EVCI owners. They are being incentivized in different forms so that a business model exists, because it's initially there will be a huge investment. So that huge investment should give some return to them. Making the prices of EV affordable. So certain tax concessions are given. If we say take the loan from the banks for the purchase of the e-vehicles, so concessional loans are also available. Similarly, there are other incentives for EV owners. Then comes the matter of economic disposal of existing automobiles if one opts for the new EV, because parking is a big challenge in the cities and as well as also in the middle class of the cities. So first, when the existing vehicle we will get rid of, the person will be in a position to acquire the new vehicle to park that. Indigenization of the EV sector. As I have told that Make in India efforts are on. So through indigenization, it is also hoped that the prices will also come down because the things will be available locally. So when the local expertise will be available, after sales service will also improve, and its repair and maintenance, or you call the O&M, will also improve. Reduce dependency on imported components and batteries. This is also part of the Make in India program. And Niti Aayog has made a big program for manufacturing of the giga scale batteries. Those batteries will be utilized in the power sector as well as in the EV sector and other applications. Development and adoption of suitable standards. This has been taken up at the national level. Bureau of Indian Standards is taking active part in this, playing active role, and so many stakeholders are part of that exercise. So in this direction, roadmap drivers, there are certain new developments. We are planning for the e-buses also, and NTPC has offered its services. They have concluded a tender of 450 e-buses recently. Then another agreement has taken place, and in the Andaman Nicobar Island, to make it smoke free, the MOU has been signed. Similar e-bus solutions for J&K, Tirumala, Tirupati, and Arunachal Pradesh are in place. EV is a new class of the consumer loads in the electricity distribution grid. So first is that we should have the EVC, or the electric vehicle supply equipment. Then we should have the sufficient network capacity of the electrical network and the power supply from that end in a hassle-free manner. So power supply reliability and quality should also be ensured. So integration of EVs in the grid management can help. It can help improve the grid quality power. By grid quality power, we mean that during the excess generation time, the electric vehicle charging can take place and the frequency usage of the grid could be controlled. It can form the distributed generation, distributed storage, and as just Vaidyaji has introduced the concept of the vehicle to grid, this concept can be used at that place. It can support the renewable energy sources, but somehow if this is the uncontrolled charging, it can lead to some damages. Those damages is in the form of increasing the peak loads, overload on the grid, and decreasing the grid power quality. Harmonics has been introduced, so I will not be repeating the same thing. So we just, I was just talking about the standards, guidelines and standards sort of the thing. And there are other plans also. This title seems to be somewhat misplaced. Infrastructure for EVs, guidelines and standards. Naturally, it will come afterwards. So here are the, what are the phases? We are working in 2 phases. 1 to 3 years, all mega cities with population of 4 million plus as per census 2011, and all existing expressways connected to the mega cities. They will be concentrated, they will be focused first. In the phase 2, from 3 to 5 years, big cities like state capitals, UT headquarters, those will be focused. So what provisions we have thought of? As a planner, we have thought of at least one charging station should be available in a grid of 3 km by 3 km. And one charging station we set up at every 25 km on both sides of the express of the highways and the roads. Further, to tackle the need of, to cater the need of the heavy vehicles, the charging stations have been planned every 100 kilometers. If required, and when the population of the electric vehicles increases, we can increase these numbers. So there will be central nodal agency for the implementation purpose, state nodal agency, and there will be EV policies. So EV policies are there. They have been framed at the state level, and at the central level, CEA has formulated the guidelines and standards for charging infrastructure. There is a provision also of the private charging infrastructure at suitable locations. So in the guidelines, there has been a requirement of, if the public charging station has to be there, there is a requirement that certain minimum number of electric vehicle supply equipment should be there in that charging station. But that will not be the case in case of the private or the residential charging stations. Setting up of public charging stations shall be a delicensed activity. Actually, lot of debate took place whether the charging stations will be requiring a separate license to sell the electricity to the vehicle owners. So for this, Ministry of Power came out with a solution that no, it will be treated as a service and a separate license will not be required. Only the PCS has to conform to the safety requirement, to the construction standards. So that is how the public charging infrastructures is being developed, that they will have certain number of the fixed number as per the guidelines. That guidelines is there, and latest amendment was brought in the June 2020. So according to that guideline, the public charging stations have to be developed. So this minimum infrastructure requirement, is listed here, that if required, an exclusive transformer should be there for a public charging station. There should be provision wherever the need arises, extension of the 33 kV and 11 kV lines to feed that particular exclusive transformers. If everything is okay, then direct connection can be taken. If those facilities are inadequate, then those facilities have to be first created and then the connection given to the public charging stations. So there should be on the public charging station adequate space for entry and exit, as well as the parking charging of the vehicles, because vehicles will take certain time. So there will be lot of crowd of the vehicles. So current international standards are also being followed in India to be in sync with the development activities. So presently CCS, CHAdeMO, Bharat 001 DC and Bharat 001 AC, these are the standards being followed. And whatsoever the kiosk or the board has been placed, that may have more number of EV supply equipment as per the requirement. Public charging station providers are free to create the charging hubs also, and they can install the additional number of the chargers in addition to the minimum number of charges prescribed. There is one more requirement, that these PCS owners, they have to tie up with at least one online network service provider to enable advanced remote online booking of the charging slots by the EV owners. And they shall provide various other type of the information by use of the IT integration technologies. The topic continued. Let it appear on the screen. Hopefully, I just want to confirm that everything is visible now.
Yes.
Yes, yes.
Yes, sir.
So there are fast charging facilities also, provision of the fast charging facilities, because a varied type of the requirement will come, starting from the simple two-wheeler, auto rickshaw, three-wheeler charging, to the car charging, as well as to the buses and truck charging. So fast charging will be required, and it will have certain additional requirement. It should have the liquid cooled cables, because the battery in the heavy vehicles will be requiring the liquid cooled batteries. And there should be appropriate climate control facility when the batteries are being charged at a location which will be used in the swapping purpose, battery swapping purpose. So we have also thought of, as there are in other parts of the world, if required, we will adopt the battery swapping facilities also, in addition to the public charging infrastructure. Inspection and clearances, they are part of the safety requirements. CA has brought out a comprehensive safety regulations amendment in June 2019. DISCOMs may also impanel one or more third-party authorized technical agencies for inspection and clearance. It is to ease out the business. Then public charging infrastructure for long distance electric vehicles and heavy duty electric vehicles. At least 2 chargers, minimum of 100 kilowatt, each of the different specifications, and with single connector gun, each in addition to the minimum charging infrastructure requirements as mandated for public charging stations. So this is the requirement of the minimum requirement of the guidelines. Over and above, anything can be placed, provided it complies to our safety regulations and the connectivity standards. Elaborate arrangement has been made in the connectivity standards. The parameters have been specified for power quality, is power quality parameter measurements and the frequency, type of the measurement, and the meters should be according to which IEC standards, all those have been specified our connectivity standards. So power quality have been taken care of as far as the regulatory aspects are concerned. And as far as regulatory aspects are concerned, the safety aspects are also in place in advance. Appropriate liquid cooled cables for high speed charging facility. So naturally these heavy duty batteries, and which are the liquid cooled batteries, they will be requiring for the buses and the trucks. For them the fast charging is a must. Fast charging stations which are meant only for 100% in-house or captive utilization. For example, buses of a company, say DTC, would be free to decide the charging specification of their own as per their in-house company requirement, that how many buses they want to charge. They want to charge the buses in a single mode, or they want to charge the buses in the sequential mode, and up to what type of the charger capacity is required, they are also free to choose that. Public charging infrastructure, expected locations and players. One school of thought is that the fuel outlets are also a type of the representative locations. So electric vehicle charging stations could also be accommodated if the safety requirement permits in the existing fuel substations. Maybe in the new fuel substations, as per the PESO requirement, that is Petroleum and Explosive Safety Organization requirement, after their clearance, they may plan the new type of the petrol pumps or the fuel stations which have the provision for installation of the EDSC also. What latest development has taken place in this? Recently, on 12th of October, Department of Heavy Industry has floated an expression of interest for installing the public charging stations across the highways. So it will be with the help of the public sector undertakings, and with those public sector undertakings that the private entities can also take part, but leader will be the public sector entities. That is the framework. CEA has been mandated to maintain a database of the electric vehicle charging stations in the country, and that we are having from different state utilities, in fact the DISCOMs particularly, we are collecting the data and updating it on monthly basis and supplying to the stakeholders. CA has also brought out one guideline. In this particular guideline, what are the main features? Only those 2-3 main features have been shown here. EDSC guidelines by CEA, that is what will be the, here the roles have been defined of the different agencies, because only one agency cannot do each and everything. It's an integration of the efforts, integration of the policies, integration of the regulations of the different organizations, making it a sum total. So the testing and verification of the equipment with respect to standard will be done by Automotive Research Association of India, ARAI. Assessment and strengthening of capacity of the sub-transmission and distribution network, it will be the job of the DISCOMs, which naturally is theirs, otherwise also by regulation, because they are bound to supply in a universal mode to supply to all the consumers who are seeking the connections in a reliable and quality supply manner. Energy performance standards, they have been assigned to the Bureau of Energy Efficiency. Then CA has prepared a report on the technical aspects of charging infrastructure for electric vehicles also. So, and these are all published and available. So particularly to address the issue of the power quality, here are some of the highlights from this particular regulations. And the regulations are basically statutory document. They have been framed under one act of the Parliament, that is the Electricity Act 2003, and they are to be followed necessarily by all concerned. So that is the force of these regulations. So here the voltage and current harmonics, they will be in compliance to IEEE 519 of the latest standard. Measuring and metering of the harmonics have also been classified, that this particular IEC 61000 class A type class A will be the measuring instrument for measure of the power quality parameters. Data will be available with the distribution licensee, and that will be shared with the consumer periodically. Similarly, bulk consumers shall also install power quality meter and share the recorded data thereof with the distribution licensee as specified by the respective electricity regulator. This slide also some part of the same regulations. Periodic measurement of other power quality parameters. Voltage sag, swell, flicker, disruptions, they will also be measured in addition to the harmonics, on which the main emphasis is there. Distribution licenses shall install power quality meter in a phased manner within 3 years. Power quality standards for charging station. Prosumers. Prosumers means who produce the electricity as well as consume the electricity. Say rooftop installations comes under this category as an example. Or a person connected or seeking connectivity to the electricity system. So there should be reliable protection system to detect various faults and abnormal conditions, and also a responsibility to isolate the faulty equipment from the system automatically. So this talks about the robust protection system. Applicant means who has applied for the connectivity shall ensure that fault of his equipment or system does not affect the grid adversely. The appropriate licensee shall carry out adequacy and stability study of the network before permitting a connection. And limit of the injection of the current harmonics at the point of common coupling will be governed by the provisions of IEEE 519. Still some remaining part of the same standard, that the connectivity standard. Measuring and metering of harmonics shall be continuous process. So here is the emphasis on the continuous process. It's not that one time you measure and go away. So it has to be a continuous process, because harmonics may come at different time of the operation of the different type of the equipment and the services, with power quality meters complying with the provisions of IEC 61000. The data measured and metered as mentioned in this regulation shall be available with the distribution licensee and shall be shared with the consumers periodically. Sorry for repetition. This just I have repeated maybe for the purpose of emphasis, that the data of the power quality shall be maintained, and not only maintained but shall also be shared with the consumer, so that consumer can also represent at appropriate place. The applicant seeking connectivity at 11 kV or above shall install power quality meters and share the recorded data. Then comes the compliance. Who will comply which provision? It shall be the responsibility of the concerned licensee to ensure that before connectivity to the grid, all the provisions with regard to the connectivity given in the regulations are to be complied with by the applicant. The user may be disconnected from the grid by the licensee for non-compliance of any provision of the regulations, and that report will go certainly up to the regulatory commissions. Provisions are quite good, but enforcement has to be ensured. as I have told in the beginning, that every electrical installation first requirement is that it should be safe. Safe for man, safe for the personnel, and safe for the network itself. So protection against over voltage of the input supply, uncontrolled reverse power flow from the vehicle to the electrical network will also be controlled. Direct current, electric vehicle charging points shall disconnect if supply to prevent the over voltage at the battery if output voltage exceeds maximum voltage limit. So if the huge voltage mismatch, in simpler terms, if the huge voltage mismatch is there, then it will be disconnected. Electric vehicle charging points shall not energize the charging cable when the vehicle connector is unlocked. So vehicle connector should be in a properly locked position. It should not be loose. It should be properly fixed up, and then only the charging should start. Earth protection systems for better power quality. Earthing of all electric vehicle charging stations shall be as per IS code 732. It is the code for the wiring installations. Residual operating current of not greater than 30 milliampere. This is the limit, and interrupt all the conductors, including the neutral, if this limit is getting exceeded. Earth connected metal shielding and cable installations shall be wear resistance and maintain flexibility over the full temperature range. Connection between the earth terminal of the supply and the conductive parts of the vehicle shall be of sufficient rating to satisfy the conditions of IEC 60364. Similarly, another IS has been mentioned where to which the power supply cable should comply with. So we were talking of the standards and their developments. So these standards have been, say, developed recently, taking help of the various available standards as well as our own operating and the practicing experiences. AIS 138 Part 1, AIS 138 Part 2, these are the standards in place. They are the standards from Ministry of Road Transport and Highway for electric vehicle, conductive AC and DC charging system. Then CEA, we call it the safety regulations. The full name you can read from here, measures relating to safety and electric supply amendment. So commonly we call it the famous safety regulations. And those who are not familiar with the regulatory procedure, they must be knowing there used to be one IE rules 1956, famous rule, IE rules 1956. So those have been superseded by these regulations in 2010, and after that subsequently there have been several amendments. And for your information, this particular regulation is under thorough review now. It will come in the public domain, and whenever required, whenever it will come in the public domain for comments, we will be requesting that your comments be offered on the same so that it could be further improved. Then there is one technical standard in the form of IS 17017. It is also for EV conductive charging system. Then for high level communication between electric vehicle and electric vehicle supply equipment, IES has adopted the equivalent ISO 15118, various parts. So this is being followed. For low voltage charging and AC charging, basic communication standard is provided in standard AIS Part 1. So just before 5-6 slide, I mentioned about the technical report by CEA, where a big triangle was there. So it is the CEA technical report. It has recommended the open charge point protocol for communication between electric vehicle supply equipment and central monitoring station. Also, the provision is that fast charging connectors and combined charging system, CCS and CHAdeMO, these have been recommended by this particular guideline. Bharat charger I have told for the low power applications. And one more thing for which the work has been assigned to us, or CEA is mandated to do this work with the cooperation of all the stakeholders, particularly the public utilities and the one who are installing the electric vehicle supply equipments and the charging stations. So we have divided a format. Format is also on the website, and we regularly write to our utilities to supply us the data to maintain as to how we are progressing in terms of the installation of the public charging stations. This is a repeat, AIS part 31. This I just explained. Then safety regulations. Technical standards, ISO 15118. This I feel is a repeat, need not be told again. This slide also we can skip. So now we are just coming to an end. So this is the last slide. So let us acknowledge that we all are on the learning path. We cannot claim that I am the expert in each and everything. But the fact is that I may be knowing something, others may be knowing better than me, and let us join hands together to make a pool of the knowledge, pool of the resources, and work together. What is required is to address the power quality, gathering field know-how or the field experience from the stakeholders. That is the key of improving the power quality phenomena in the country. Unless the feedback will not be there, we will not come to know what is happening. Because harmonics in the system will be there, neutral currents will be flowing more, there may be burning of the installations, there may be overheating phenomena and other type of the disturbances. So this all should be recorded, this all should be known and should be utilized by the designers and the planners for a better managed and the better planned network. High standards will set a strong foundation for the PQ. So standards I just tried to describe. So those standards are being developed on a continuous basis. PQ is a critical to ensure reliability of electrical network and avoid unforeseen challenges. To ensure good power quality, we must join hands together, and I hope we are all together. So that's all. In the next slide, I am giving just my phone number is also there, email is also there. Please feel free to provide feedback and suggestions. And thank you to everyone. Thank you for patience listening. Thank you to the organizers who gave me this opportunity to present my talk here. Thanks.
Thank you, Ashok ji. Thank you, Ashok ji. That was a very informative session. Some of the questions I thought also got answered. So thanks a lot for that. Before moving on, we have another survey, but before that, we have shared the survey results of the first poll, and then I think we can roll out the second survey before we move on to EPCO's address. Yeah, so the next survey question is on your screens. So have you experienced any instance of poor power quality? So we have closed the poll, and you can see the results on your screens. With this, I would like to now invite Echo to address the forum. While he's sharing the screen, we have got a few questions already, and thank you for those. We will try and get them through as many as possible. And thanks for your patience to stay till the question answer session. Yes, we can see your screen. You can go
Okay,
ahead.
thank you very much. You can see the whole screen, the full screen?
Yeah.
Okay, thank you very much. So I was just triggered by the poll that it said that 70% of us did not mention any power quality issues yet. So I'm going to show you some practical cases about power quality, what I've experienced. And yeah, the major thing for me today is to let us understand the importance of power quality. And as I say on this first slide, it's a ghost. You don't know where it is. It might be there. It might be gone. It's yeah, you cannot really touch it, but you can measure it. And that's what I am going to tell about the standards. First message to policymakers and standards from please give more focus on currents in standards, because most standards are viewed by the voltage, but when you look at the impact on power quality, it's all done by the current, of course, because the supplier, the grid supplier, is giving voltage, and the customers are pulling out current out of the grid. So we're going to look at the impact of EV charges to power quality. And you have different kinds of areas. We have buses, they're mostly connected to high voltage areas, and we have bicycles, and they are connected to the residentials and homes. I've divided these connecting areas in 4 places. That's because also the power quality issues on every place is different. So I like to tell a lot about the power quality, but I have only time for 2. Let me say, I have only time for these 2. So when you look at an evaluation, I'm looking at the point of coupling. The point of coupling is on buses, is high voltage grids. I'm looking at the strengths, the weakness, opportunities, the threats, and what kind of focus I will give you for power quality. So when you look at the left side, at the buses, it's connected to the high voltage grid, is high power, mostly DC. Mostly it's immune for noise because it's connected to the high voltage grid, and it's pretty predictable because you know where the bus is coming. And I've heard also talking about a dedicated grid, a dedicated transformer. So that would be yeah, pretty easy to manage. There are also some threats. In the Netherlands, it's not allowed anymore for buses to park under high voltage lines. That's because when a bus gets burned, then the high voltage lines will become hot and they will drop on the ground. But when you look at the power quality issues, yeah, they're mostly related to is there enough energy? What is the best place we want to put the charger? But the best place where we put the charger can be the worst case for the power quality, because it has long lines, it is a high impedance. So the best place for the charger is not always the best place for power quality. But when you have a focus on power quality, you should look very good to the energy management, and that is mostly demand side management. And that's also the case for the mid voltage grid chargers, fast charging cars, fast charging bigger trucks, also direct current. And I'm going to focus on the right two sides. Those are the one-phase chargers and the three-phase chargers. And this, I think it's very interesting to see. So when we go back in time, in 1906, we had the first electric car, and then we did not have power electronics yet. So we had a step-down transformer and a rectifier, and then we got out a direct current. But nowadays we are looking at lower weight, higher efficiency, and that was the time that the switch mode power supplies came. So we exchanged the copper transformer. We exchanged the copper transformer for sand, so silicium and germanium, which we built power electronics. But the switched mode power supply has also some disadvantages, and that I will express them. So how does a switch mode power supply or a switch mode power supply charger look like? With the differences, the old chargers is that normally the grid would see an impedance, and now it's looking at the capacitor of the input of the switch mode power supply. So that's a very big difference. And what also is different is that the old chargers were 50 hertz in and 50 hertz out, and the 50 hertz were made a direct current. And nowadays we have 50 hertz in, and we have loops of 30, 60 kilohertz, and that's also signaling back into the grid, and which makes a lot of problems. So let's look at a practical situation. We have 3 cars, and now I have connected the 3 cars that are 3.5 kilowatts each onto a grid. So at the top left, you see the switch mode power supply charger, which is giving current as the car likes to the battery. And in the left screen, you'll see the sinus wave, and with the little spikes over here, this is the current. This is the current that's coming. This is done. This normally what you would have a old transformer. The current follows the voltage, but now the current is only drawn at the highest point of the voltage. So we will get flat topping for that. So when you look at my screen, then you see now we have 41 amps in the phase and 41 amps in the neutral. So that's logic. Now we're talking about EV chargers, but also, of course, your LED lights, your laptop, they are all switch mode power supply. So this is not unique for an EV charger. It is very common that we also everywhere in the grid we used switch mode power supplies. So now I'm going to add another phase. So now we have 3 cars pulling 41 amps out of the grid. Let's look at the currents. Current phase 1, current phase 2, current phase 3, and the neutral wire. So now I have 2 phases and 1 neutral. And now you see 41 amps in phase 1, 41 amps in phase 2. And the current in the neutral is it's higher. But normally when we have 3-phase systems and they are in balance, and we also have the current and the voltage factor, which are 120 degrees forward and backward to each other. Normally, when you would have a 3-phase system and in all lines you have the same current, then the current in neutral is almost zero. So let's look at it. Let's put on the third phase. And what you see now is that there is more current in a neutral than in the three phases together. That's terrible for the system, because when we do a cable calculation or a cabinet calculation, normally in the 50 Hertz area, or in the 50 Hertz period, we would divide the neutral by half. So for example, the phase is 70 millimeters and the neutral is 35 millimeters. But what you see here is phase 1 is 41 amps, phase 2 41 amps, phase 3, and the neutral is 71 amps. How is that possible? Now, that's possible because of the third harmonic, and that's killing cables, that's killing cabinets, and it's heating up connectors. So this 71 amps is a problem. Does the fuse blows? Mostly not, because most systems have fuses in the phases and not in the neutral. So when you look at the harmonic picture, I have put some arrows at the place of the third harmonic. So the third harmonics, the multiple of the third harmonics, you could add them on top of each other, because that is at the same time this third harmonic and the 9th harmonic and the 15th harmonic, at the same time they are pointing the same direction, and that is why the amps in the neutral will be plussed over there. So we have 41 amps going into the chargers, and then 70 amps they're going out. So that's terrible. When you look at these pictures, I can instantly say, okay, these are one phase chargers. That's because one phase chargers, they have 4 diodes. And when you remember the number 4, you plus 1 and you minus 1. And when you have 4, you will see the, sorry, the third harmonic is not, but you will see the third and the fifth harmonic come up. But what if we would cut the wire? Or what if we, what if the neutral wire is melted? It could be so that in a cabinet, that the neutral wires would get so hot that it melts down, or the cable is lost. But then the system will keep on working. I will show you. Here you see the third harmonic has vanished. That's because the neutral wire has been cut or melted down. And now you see the 5th and the 7th harmonic coming up, and the line current has dropped a bit from 41 amps to 35 amps. But the chargers are still working and still delivering 3.5 kilowatts. So when I'm looking at this picture, this harmonic picture, I'm seeing the 5th and the 7th harmonic. So that means that the grid is looking at normally would look at a charger which would have 6 diodes, or a 3-phase charger it would be. So on the left side you see the voltage and the current, and when the neutral wire is cut or melted down, the grid will look at it as a 3-phase charger, and that's why the 2 bulbs are there. Vikrant, can you also see my my pointer?
Yeah. It's a little dim, but yeah, now we can see.
Okay, that's fine. Thank you very much. Yeah. So one slide back, here we have the 3rd harmonic and the 9th harmonic and the 15th harmonic are gone because our neutral wire was cut or melted down. And here are our original marks. This is the 3rd harmonic, and this is the 9th harmonic. So now when we are cutting the neutral, this will happen. So here you will see the 9th and the 3rd harmonic has vanished. The 5th and the 7th harmonic are still there. So that means what I said, the grid is looking at a 3-phase charger. There's nothing wrong with that. But when the neutral is coming back, then there's something happening in the grid because it has to be balanced again. And the neutral, the middle of the star of the 3-phase system is floating. And when we are connecting back the neutral, as you can see here, you get some transients of 323 amps, and you also get, because you draw a high current out of the grid, you also get voltage transients, and they are very bad for your grid, because other equipment could be damaged. So normally you would have 40 volts, 40 amps, 40 amps, and when the neutral connector is disconnected and connected again, you will get the inverse current of 10 times almost the nominal voltage, the nominal current. So when I look at evaluate the low voltage AC side and the chargers, the 1-phase chargers, they are universal, and which means that they are almost immune to THD. When you have a voltage drop till 90 volts, for example, the switch mode power supply chargers will keep on working. They will just higher the switching frequency, so they will keep alive. That might be bad in the future grid, because when there is a big voltage drop in the grid, the standard should say, okay, a big voltage drop between 10% of the nominal voltage, then the charger has to go out. But you can try this at home when you have your PC or your laptop, for example, and you lower the voltage to 80 volts, everything will keep on working, but the current will go up, and that means that unregulated 1-phase charges connected to the grid, and you will have a sag in the grid. It will multiply the power quality issue. So what's very important is the 3rd harmonic. That's the real weakness of the system. And that's because you have 4 diodes, and you have a lot of 3rd harmonics, and that's giving a lot of extra current in the neutral. Also, when you have long lines, high impedance, long resistance, then the end of the line, the voltage will not look as a sinus anymore. In the old days, at the end of the line, we could have a lower voltage, but with switch mode power supply, it could also mean that in the end of line you will have much too high voltages. And what is very terrible is the DC offset, because the DC offset of some chargers, when some chargers break down, for instance, a diode is damaged, you will get DC offset. And in the residential homes, you have the earth leakage current for the protection of our bodies, and those earth leakage switches, they will saturate, because you will get, when you get a DC current through a earth leakage switch, it will saturate and it will not react anymore. What's another opportunity is very easy. I've seen bad chargers, good chargers, and just say in the standardization that the power factor has to be almost 1, and then it will be fine. There's a big threat in cables. When I'm going to accidents, it's of course we have the 3rd harmonic. Of course we have all kinds of problems with the harmonics. But when there are problems with cars, it's mostly because they burn out. And that is, I see that especially at the connectors. The connectors, they lie on the ground, they got dirty, And when you look at the inside of the connector, for example, at the Mennekes connector, you look at the inside, it's totally green. It's copper that is has corrosion on it. Copper is one of the best materials, and it should be taken care of very good. But it's corrosion that's killing the cable. There are also some cables which are made of aluminium, and that is aluminium cables cannot handle high temperatures. And what's happening with a copper cable, when a copper cable gets hot, gets very hot, say for instance 200 degrees at the connector point, and then the temperature drops down again, copper has the capability to come back in its original form. So when you heat up copper and you cool copper, it will come back to its original form. When you have aluminium cables in the transport for electrical cars, they are very nice because they are very lightweight, right? So that's a good thing. But the bad thing is that aluminium cables, when they get hot, very hot and then cold, they do not get back in the original state. And the next time they get hot, they get even hotter because the resistance of the aluminium has risen a bit. And the next time, it will be a weak spot in the cable. So be very careful when you're using aluminium cables. So when you have a focus on power quality issues, one phase, for the standardization, just make the power factor 1. That's beautiful. And over design the neutral, because it's not only EV chargers, of course, that are connected to the grid. It's also PCs, everything in your home these days has a switch mode power supply, even your fridge, television, etc. So look out. So now we're going to the next one. That's also interesting. That's what Asrak also mentioned. When you look at the future of power quality, and you look at the design of a 3-phase car charger, it could also be a harmonic filter. When you look at the design of a harmonic filter, an active harmonic filter, it's almost the same than a car charger. So the designers should make it two-way, and the standards should be allowed to inject harmonic currents into the grid, so that it will be rebuilding the sinus. So it will be rebuilding the signal. So when you have bad quality in your system, sags, harmonic distortion, name it, and you have super good engineered power supplies which are connected to batteries, they can act as harmonic restorers. So that's a message for the guys. But who's going to buy a car for 30,000 euros and a very, very expensive inverter in it? And there's another thing I want to mention. I like to buy a car with a very good charger, which can rebuild, which can inject harmonics into the grid to get good power quality. But what would the car manufacturer say? You are using my battery from the car, and that is lowering the warranty of the car. So you have a split intensive. For me, it is put good power quality. And the manufacturer of the car, he will not allow it, because then his warranty of the battery will expand. So that's terrible. But look at now we go back to practice. This is another area. This is a Tesla Model S, and we've connected some Tesla Models S to the grid, and I'm going to do the same thing with the one-phase case just now. But first I will show you that the voltage, as you can see, 414 volts, THD, very nice. So what you're giving the inverter, that's what he will be using. When your THD, your voltage is very, very bad, of course, it will also draw and put out very bad current. So let's take a look at the three-phase switch mode power supplies. The voltage is good. And now I'm looking at the current, 160 amps, flowing through every phase. And here you see that the neutral wire is 13 amps. So I've tried to look where is that 13 amps coming from. So as we can say, the 160 amps is for power charging, and the 30 amps is just for electronics, transformers, the controller of the EV. So after that, I'm looking at the power quality, and remember, we had a total harmonic distortion with one phase charges of approximately 120%. So that is a lot. So now look at the total harmonic distortion of three-phase chargers, and now you see it's only 6%. So that is very nice. And for now, I'm looking at the amperage at the current harmonic distortion, not the voltage harmonic distortion. When I'm looking at the voltage harmonic distortion, let's go back. It looks beautiful. It looks beautiful. But when you look at the current harmonic distortion, it still looks good. But Manas said I could not show you a video. But what I must say is that the 11th harmonic and the 13th harmonic are jumping up and down, So I pulled out a Tesla, put it in the laboratory, and checked it out, and it was not jumping around. So first, as you can see on top of this, we have 1, 2, 3, 4, 5, 6 diodes. 6 diodes, 1 minus, 1 minus. And that means we will have to see the 5th and the 7th harmonic, because this is a number of 1, 2, 3, 4, 5, 6. And then, so you can see over here the 5th and the 7th. So our inverter has 6 diodes. Remember, we were talking about the one-phase inverters. One-phase inverters have 4 diodes. So the 4 diodes, 4, 1 minus, 1 plus, then you will see the 3rd and the 5th harmonic. So when I'm looking at this harmonic picture, I can instantly say, okay, this is a 3-phase charger with a 6 diode bridge. When one diode is damaged, for example, so this diode is damaged, you will have 5 working diodes, and then you will see even harmonics. Because when you have 5 minus 1 minus plus 1, you will see the 4th and the 6th harmonic, and that's because you will have a sinus that is, I don't know how it means, but it is on an angle. So I think this is pretty good when you compare it to 3-phase chargers. Normally you would see here at the current 2 bulbs, but in the chargers, I've opened them, of course, and there are so a lot of coils, and the coils they are good for power quality. What I was still wondering about is, what is this? The 11th and the 13th harmonic are jumping up and down, and it is even jumping so hard that it is going out of my reach of my analyzer. So let's investigate that. So what I used, normally I would use a fluke current clamp, but when you're looking at the power quality in depth, you will need a high frequency Hall generated current clamp, or just a shunt. Shunts are the best there are, and then you can measure it very good, but I cannot measure high frequency with a low frequency current clamp. So I use this current clamp, and I connected my oscilloscope, and I checked the phases and the neutral. And what I saw over there, here you can see we have 550 hertz. That's this one. So that's the 11th harmonica, and it's jumping up and down, up and down, up and down. And it even has when you let your oscilloscope make a snapshot, it will calculate that it has an amperage of so the nominal, the big signal is 130 amps, 130 per phase. And when you divide that, then you will see that it's about 5 or 6 amps at 550 hertz. But what was confusing was that it's going up and down, going up and down. Because outside we have a lot of chargers and they are just standing there and nothing is happening. Nobody is driving away. So it's not coming from the chargers area, it's coming from somewhere else. So let's investigate how this 11th harmonic and this 13th harmonic, where they are coming from. You see, and you look at the signal, you see all these spikes. It's not a neat voltage anymore. When you look at the power quality analyzer of Fluke, which has low resolution current clamps, you will not see, you cannot look into the sinus. And that's interesting about high frequency current clamps, which also can measure direct current. Of course, with just a coil without a Hall generator, you cannot measure direct current. So let's look where this is coming from. So first we are going to do a broader view. This is at the company in Kampen in the Netherlands. It's Tembo, and it has a few roofs, and on the every roof you have solar panels. Here we have a solar panel area of 220 kilowatts, 220 kilowatts. We have a transformer, a main cabinet, sub-cabinet, and the sub-cabinet there. Here they are connected to the charging area, which I did my experiment. What they are doing there, they are making paper straws, so we will get rid of the plastic in the seas. They are making high efficient machines, and they are making washing machines to pack them. But what I was looking at the industry side of this area, we had no problem at all, no problem at all. And on the building side, we had passive infrared detectors for the lighting. They broke down. We had heat pumps, which we had problems with the communication. We had a fire detection that, during the day we had a fire detection and we didn't know where it was coming from. And at some days during the day between 12 and 2, the charges would not charge. And that was interesting, because what is special about this installation between 12 and 2 o'clock? That is the sun. So I looked at the inverters, at the electrical system. Here we have the transformer. This is our measuring place, and this area is covered by inverters which has coils, and this roof has transformerless inverters. So the only difference between this area and this area is that here they have transformers in the inverters for solar, and these transformerless inverters have less coils. So I was looking at not the voltage but the current, and I was following the current where that 11th harmonic and the 13th harmonic were talking to. So then I found at the cars, we just spoke about it, we have the 11th harmonic and the 13th harmonic jumping up and down. At this cabinet I could not find a thing, but as this cabinet, hey, I found the same. but the phase was in the opposite direction. So that means that these inverters are talking to these chargers. At the current from around, it's jumping up and down, but 16 amps. And 16 amps at 550 hertz, that's really terrible in your cables, and it will destroy a lot. So now let's go a little bit deeper into the signal of the solar inverters. And what you can see is that you go very deep in there. You will see that it's charging. The switching frequency of the solar panel inverter is around 16 kilohertz, and that is also the switching frequency of the EV charger. So what I did, I shut down the solar panels. I just switched them off, and then all cars started charging again. So that was sometime we were a little bit lucky to find it, because somebody said we only have this problem when we have the biggest production of solar energy. So, and not only, of course, between 12 and 2 the sun is shining. In the morning and the afternoon the sun is of course it is shining, but then the inverter of the solar panels have different switching frequencies, and when the switching frequency of the solar inverters are different compared to the charging frequency of the EV chargers, there are no problems. And the problems, they were, and all these problems, not charging cars, the fire detection went off, lost communication with heat pumps, breaking down lights which would not detect anyone coming in anymore. All these 4 things, when we evaluated with the people there, they all said, yes, it's true. It happened between 2 and 4 o'clock. So here we found the things. It was also very easy to solve this, because I went into the parameters of the solar inverters, and I just adjusted the switching frequency, and then the problems were gone. So coming back to this slide, when we look at the 3-phase chargers, the strength is that they have a low total harmonic distortion. The power factor, it's very nice. But what I found, and I would like to ask Ashok in the panel meeting, yes, there are standards, but most standards are for components or only the grid, only the charger. But I've never seen standards for systems. So how could, and I think it's also very difficult to do, because not only the chargers have their own switching frequency, but in the building of course you have a copy machine, you have LED drivers, and what is in there, EMI filtering. The EMI filtering, it might not only filter itself, but the EMI filter could also filter the grid. And when the EV chargers are putting in terrible harmonics, the EMI filters from the rest of the installation will eat them. What's an opportunity for these cars, 3-phase systems, is that they can become an active harmonic restorer. And it's when you have problems in the area, just look at the switching parameters. and just adjust them, and then you will get rid of the problems. What's also a threat is the connectors, just like the one-phase connectors. And in the factory, we also had some old machines, and they had passive filters. But passive filters, they are designed for a specific, for example, for a specific harmonic order to compensate. And that's a static situation. But when the sun is shining, a cloud comes, an extra car is connected to the grid, the passive filters cannot adapt. And you have a lot of resonance or interaction with all kinds of electronics in the same building. And I'm warning India, this building is, I can overview this building, and I can get into every cabinet in the building, and the building is not so much alive. But when I'm thinking about New Delhi, a big city, a lot of consumers, maybe a lot of prosumers, solar panels, EV chargers, then I would be very scared and see a lot of ghosts, which I would call resonance and interaction. So that was will be my question to Ashok. Are there power quality standards for the total system, so that components will not interact with each other? So this was my presentation about power quality. My meaning is that power quality will certainly play a crucial role in the ambitious EV roadmap of India. And I've heard Ashok talking about the dedicated transformers and the dedicated grids. That's a very good thing. But what I'm afraid of is the interaction between whole systems. So this was my presentation, and it was nice to be here. Thank you.
Thanks a lot, Epco. Very deep technical and enlightening material. Thank you. So I think let's question to Ashokji. Let's probably start with that. And in the meanwhile, we will also have our third survey parallelly running. So Ashokji, over to you. As Epco was asking, are there any standards at system level instead of the subsystem or component level that are in the pipeline or under implementation?
Actually, regulations are for system level. That in the system at different points, this should be the power quality criteria. And as far as BIS standards are concerned, they are the standards at the component level. Hello.
Yes, thank you.
Yeah.
So the I cannot see the screen anymore, so I'm a little bit confused. Oh, yes, I see the same screen now. I cannot see the screen anymore.
Yeah, the survey which was running parallelly, that is probably appearing on your screen right now.
Yeah, that's right. Yeah. So Ashok, there are standards in India that regulate the interaction between different kinds of chargers and inverters. At the current point of view.
Pardon, kindly repeat.
Are there standards? So you said there are standards, but are they also the cases we had? For example, the EV chargers and the solar inverters and all the other equipment, they were according to the IEC standards, but the interaction between all those components, that is what you are working on now, because in Europe we do not have standards which regulate the interaction between different machines, for example?
Actually, for that, I feel communication protocols are there. One is that ICPP between EDSC and electric vehicles, and other standards communication protocol from vehicle to the EDSC.
Yes,
it is
okay.
basically, in my view, it has to be the total system integration, because that network service provider is also one concept which we have built into our system, that he has to have, PCS owner has to have the services of a network system operator, dedicated network system operator. So from his PCS, the data will go to the central location of the DISCOM, so that it could be centrally controlled if required.
Okay.
And another is the standard communication protocol, which is playing part for the purpose of charging of the vehicle. So between the vehicle and the EDSC, standard protocols are there. Whatever are being followed internationally, that we are following, we have not developed any new one.
Oh yeah. No. And what's also the case, at the point of the transformer connected to the DSO, to the grid, we had no problems. So at the transformer place, where confirming your regulation, we should put a power quality analyzer. The power quality at the transformer at the point of coupling is very good, but in the building, in the street, in the industrial area, inside, there it is terrible. But it, of course, it is a responsibility of the owner of the building or the area, to regulate that, because the only one who is suffering from bad power quality is the owner itself. But the injection to the grid is minimal, because the transformer, it fades away almost every power quality problem, excluding sex. So the standard you're talking about, they mostly focused on the connection where it is going from private to public.
Actually, in addition to the regulation I described, there are standards of performance regulation to be followed by the utility also.
Okay, good.
So there are standards of performance which talk of the primarily of the voltage fluctuations and many other things. Other things are of course out of our present topic. Other things are that in how much time, if the transformer has failed, it will get repaired. So that is naturally not related to this particular topic, but indirectly it is related. Say if one transformer has failed or some cable section has gone out, on the rest of the part there will be extra loading, so that way it is affected. And that voltage at the point of supply of the consumers, that voltage range is fixed. Say it is 230 volt, so it could be 230 volt plus minus 6%. That has to be maintained by the electricity supply company. That is one.
Yes. Okay.
And otherwise also, if say a lot of reactive power issues are in the network and the voltage is going down at particular locations, then properly rated, adequately rated either switched capacitor or the fixed capacitors of certain ratings are to be provided to maintain the voltage level.
Yeah.
And bulk consumers has the responsibility, as I was telling that our regulation describes at one point, one clause is there, that it is the responsibility of the bulk consumer to install the power quality meter and share that data with the regulators.
Yeah, but with the coming of a lot of EV chargers, and then you will also have to make a transition from passive filtering, like capacitor banks, to active filtering, which can react on the loads. Because what I've seen here is that a lot of capacitive passive banks, they blow out because the power quality issues are very dynamic and not static anymore.
Naturally, not much work has been done in this direction. So certainly we'll be learning and we'll be taking the experiences of the other stakeholders and the other countries also. That is one. And one more thing is there, that the harmonics problem in say supply network are not only because of the PCS, public charging stations, or the electric vehicle supply equipments. It's the combined effect of the other loads and the combined effect at what period of time during the day they are coming into the service. Suppose there is a factory or a workshop where lot of welding work is going on, welding machines. So maybe that is working during the daytime, say from 9 to 5. So that time the harmonic content in the supply network will be more. So it would be very difficult to identify whether it is due to only that particular load, that is the welding load, or also because of the, or separately because of the electric vehicle supply equipment. So whatever will come in the network will be the combined effect of both. So that's why we have given insistence, or we will give further insistence when the population rises. So far lucky that that much population is not there and we are not facing as such any problem, because the adequate margin is available in the distribution supply network, particularly in the urban areas. The distribution supply network of India have quite good margin. So that is catering to the supply conditions. And what has happened, earlier we used to be power deficit country, but now there is no such scenario, and particularly in the urban areas, metro areas, we have adequate and reliable supply, reliable power supply. So those power cuts and all those things are not there. So it has to be a part of the study, specific study has to be carried out. When the harmonics are likely to be more in the network at what time? Say here, mostly the office goers have the vehicles. And similarly, the shop owners also have the vehicles. So their timings are different. There is a diversity of the timing. Say offices are mostly 9 to 6, 9 to 5 or 9:30 to 6. Whereas the shop owners timings are generally 11 to 8. So that's why there is some time gap in the usage of the electric vehicles, and similarly the charging pattern. And another type of the load peculiarly in the country like India is that of the two-wheelers, three-wheelers and the auto rickshaws. They are large in number. So their charging pattern is like this, that during the night time, they get charged at a concentrated, at a fixed place. So there comes the concentrated load. And that is, I am not saying a way to say, somewhere they are in an organized way, somewhere they are in an unorganized way. And also getting charged at the residencies of the owners. So car charging, they basically the usage pattern has to be studied. So this simply is, it could not be a simple answer. Say I say that because of this and at this particular time there will be an issue. A lot of statistical study has to be done, and the pattern need to be analyzed, supported by the measurement techniques. And another type of the vehicles, this EV charging load is because of the private taxis running on rent. So their pattern is entirely different. Their pattern is that they want to optimize, they want to maximize the mileage out of whatever charger or whatever fuel they have. And whenever there is a peak time, say peak time is in the morning, early hours of the morning for the flights. So everybody from the center of the city would be going towards the airport. So that time they would not like to charge. So they would be charging it in advance at particular time of the day, whatever suits to them, so that their passenger load does not reduce. They do not get deprived of their passengers. So there are many factors. And another is we have in our tariff phenomena here the time of use meters also. So far it has not been widespreadly used, but the concept is there, and this concept we are thinking will help in segregating the charging loads in managing the peak.
Thank you. Thank you. There are a couple more questions. We are over time, but just wanted to have those, and then we can have conclusion. So one of the questions is kind of related to the discussion we were having, which is about what will be the tariffs for public charging stations, and will there be any penalties if they introduce harmonics due to their usage? So that is one of the questions to Ashokji.
Yes, this I can reply. So far in the electricity tariff, no penalties are there for the tariff because of the EDSC. For the power factors, there are tariffs. And for the industrial loads, say induction furnace and like that, so there are mentions of the penalties for the harmonics. But right now, not for the EVSCs, but time will come that when there will be a penalty, like the low power factor penalty is there. So that type of the penalty could be inbuilt. That is one. And another, what was there? Question was in two parts.
Any special tariffs would be employed for public charging, or they would be similar to the utility tariffs?
Yes, it is quite specific. There is a cap on the tariff. It will be as per the tariff policy notified by the central government. And till the time the tariff policy is notified, whatsoever comes so far, it has to be notified. Till the time the tariff policy comes out, the tariff will not be more than 15% of the average cost of supply for that utility. Is say one utility is supplying at the rate of X per unit, so X plus 15% could be the maximum charge which the utility can charge from the public supply owners.
I can add something in Europe about that, about the tariffs for a kilowatt hour. The slow charging tariffs are very close to the original utility grid, and the fast charging tariffs are when you charge 10 times faster as home, then you will have to pay 10 times higher for a kilowatt hour. So a kilowatt hour in Europe is 3 to 4 cents, and when I'm fast charging 10 times faster at the DC level, very high power, then the money will also be 10 times higher for the same kilowatt hours. So my battery charged at home is about 2-3 euros. And when I'm charging on the move, the same battery in a faster time, I will have to pay 25 euros, 10 times higher. So the speed of the charging is linear to the extra costs in Europe.
Okay. Thank you.
And one more thing regarding this tariff, basically the domestic charging, wherever the domestic charging is there, residential charging, they will be charged at the domestic supply rate, and the PCS have to maintain a separate meter also, so that exclusively that could be metered for the tariff purpose.
Okay. All right. Sorry, we have very little time, so we would have to finish the question answer session here. We are already past 6 o'clock here in the evening. So, Manasji, I would request you to give your concluding remarks, and then we will try and circulate these questions which have been asked. I see some of the people have been asking since some time. So, yeah.
These
Manasji, over
questions
to you.
can be emailed,
Yeah,
Vaidyaji. These
yeah,
questions can be emailed, and to
yeah.
our whatever best possible knowledge, we will try to answer.
Yeah, absolutely. Thanks a lot. Yeah. Over to you, Manasji.
Great. I think it was fantastic session. Only thing we really overshot the time, but it's worth it. And though we are little limited people, from 63 we came down to 49 now, but I am sure all the people who are attending and still having the patience are definitely having the worth of their time, of which we sincerely appreciate. Just quickly, I wanted to have the key learning from today's session, which I could gather, and I'll put it into a slide and post webinar all these slides as well as the webinar recordings and the question answers will be structurally posted onto the EPCO website, and webinar recording will be shared with each of the registered attendees. So please don't worry about it. And I must say that it has been a learning, even for people like us, and including the experts by exchange of their opinion. So basically, EV chargers, what we are seeing, it can create unusual PQ challenge, and it can be the largest load in case of domestic people, and very large load in case of public, and their location, their monitoring will be extremely important, because PQ will be intermittent and it will be all about the compatibility, and you expect changes with new loads like EV, RE, which are introduced into the system, and our total vision regarding system design has to change from product orientation to a system orientation. The standards are basically accumulated wisdom. If everything is going right, we don't require standard. That itself is standard. So when we formulate a standard, we address varieties of options to solve our problems. So it's the key to our way forward. We don't have anything for EV chargers yet. And EV charger, whether they're compatible with voltage dips or the kind of swing what EPCO has shown into those measurements, that's something interesting to ponder about when we are aspiring to be a EV world leader as far as usage is concerned. EPCO, one of your observation, of course, on the survey, basically EV penetration in India is very low at this point of time. It is just in the beginning. So you got that answer that no, PQ challenges have not been faced because we have not really seen that. And we have to really, time has come to rethink on what it takes to have robust distribution infrastructure for accommodating the new age loads. Some of the thoughts we have to think over. PQ mistakes can happen while designing power electronics of chargers. EV chargers can be bidirectional, like as you indicated, it can be the electric harmonic filter. Also, it can also have the storage facility. And when it happens, load versus source, that debate will come, and we need to think around it. And when PQ immunity design has to come, it will obviously increase the charger cost. So the financial considerations, who will bear with it? And that question will obviously come before our policymakers. And in solving all these myriad issues and challenges, the EV technology community and the conventional power distribution grid community has to work together to address above. We cannot work in silos, and just go ahead that whatever we are doing right, and we can meet only then the social demand, because in each geography, what is good in eastern region may not be good in western region, what is good in western region may not be good in southern region. Depending on the geographical region, we will also have to have variation into our approach to secure the assets which at enormous cost we are going to put in our country. And if those assets are not sustainable, including our distribution infrastructure, we'll have a terrible time, which we are little bit still lagging from developed world, and probably we can leapfrog by learning from them, which is visible. And implementation is another key issue. We are having world-class policy, we are having world-class standard, and we are having world-class regulations. One of the thing Ashokji mentioned, that the discounts will inform. But if we really see whether the discounts are truthfully disclosing every data, whether we are getting all information automated, whether they are transparent. So if the implementation is not done right, will not be having sustainable action like in all cases. So with those few observations, I thank you, each one of you, EPCO, Mr. Rajput, Bikramji, and each one of our attendees, including our green room boys, Pranav, Ashutosh, and everyone, to bring this to the APKI community at large and share the word once you get it. Have a great weekend, stay safe and stay healthy. So with this, we declare today as a closure. Thank you very much.
Thank you very much. Nice day.
Good day.